Hi everybody, welcome back to the Feynman technique. Today I'm going to show a new method of solving the Gaussian integral using Feynman integration. I've already solved it using Feynman integration one way, but we're going to use Feynman integration another way. I'll try to remember to link to the video in the other demonstration using Feynman integration, but you can find it on my channel easily enough if I forget to do that. So our first thing is we're going to define f of x to be the integral from 0 to, let's see, x of e to the negative t squared dt squared. All right, this is just the setup. We're going to let some other function g of x be equal to the integral from 0 to 1 of e to the negative x squared times t squared plus 1 over t squared plus 1 dt. Okay, and then we're going to let yet another function, h of x, just be equal to f of x plus g of x. All right, now let's take the derivatives of f and g with respect to x. So f prime of x, we'll use the power rule and we'll use the chain rule. So this is going to give us 2 times that integral without the square times the derivative with respect to x of the inner function. Now you'll notice this is just one way of writing the antiderivative of e to the negative x squared. So when we actually take the derivative of that antiderivative, we're just going to get back e to the negative x squared. So we have 2 e to the negative x squared. Okay. So there's our f prime of x. Now let's figure out what g prime of x is equal to. Well, it's going to be equal to the derivative with respect to x of this. It's equal to d dx of our original g of x. And we can use the Leibniz rule for differentiation under the integral sign to bring that in. Okay. And now let's mess around with this a little bit. If we take the derivative with respect to x of this thing, really this is the only thing that depends on x. So it's an exponential, so we're going to get it back, and then we need to multiply it by the derivative with respect to x of this. All right. Taking the derivative with respect to x of this, well, t squared plus 1 is a constant, which is going to cancel this. And then all we have to do is take the derivative with respect to x of negative 2x. So we're going to get our negative x squared, so we'll get negative 2x. So there is our g prime of x. All right, well, we can actually bring out this e to the negative x squared like this. And let's see, now we can make the substitution that u is equal to xt, implying du is equal to x dt. And we actually have an x dt right here. All right, so our g prime of x is now, let's see, x dt is just du. X squared t squared is just xt squared, which is just u squared. And let's see, if we plug in 0 for t, we get 0 for u. And if we plug in 1 for t, we get x. Okay. Great. All right, so there's our g prime of x. All right. Well, that's interesting because that is exactly our f prime of x. So we have um, f f prime of x plus g prime of x equal to this. Sorry, this plus this. This right here. And now you'll notice those are exactly the same thing, so that is just 0. Great. All right, now let's reintegrate this equation right here with respect to x. So we're going to take an antiderivative on both sides with respect to x. That's going to give us f of x plus g of x is equal to some constant c. And now we need to figure out what that constant c is. Well, let's take a look at our original f of x and g of x. What if we let x equal 0? Well, let's see. F of 0 is certainly going to be 0 because we will have integral 0 to 0. So f of 0 is equal to 0. G of 0 is equal to, well, if we plug in x is equal to 0, we're just going to get a 1 on top. So we'll be left with the integral from 0 to 1 of 1 over t squared plus 1 dt, which is pi over 4. Okay. So, let's see. So f of 0 plus g of 0 is equal to c, which is equal to 0 plus pi over 4, right? Implying that c is equal to pi over 4. So we've just shown that f of x plus g of x is equal to pi over 4. All right, and now what we're going to do, well, this holds for all x. So what that means is if we take the limit as x goes to infinity of f of x plus g of x, it still equals pi over 4. But that is also going to be equal to the limit as x goes to infinity of our original definitions for f of x and g of x. And I'll go all the way up here and copy them in. So, of f of x plus, and then our original g of x is this. All right. So let's see. That means that pi over 4 is equal to what we get when we evaluate this limit. All right. So let's just, for this one, we can just plug in the limit. So we're just going to, the limit as x goes to infinity of this thing is just going to be this thing when x is infinity. And if we plug in x is equal to infinity, you'll notice this term will go to 0. That means this entire thing goes away. And now all we do is take a square root on both sides, and we get square root of pi over 2 is equal to this. And we change the dummy variable back to x. And there you go. There is one more way to solve the Gaussian integral. I hope you enjoyed that, and we'll see you next time.